Everyone, this is Shravya. I'm currently pursuing BE second year in Sri Venkateshwara College of Engineering, Bangalore. In this video, I'm going to discuss about the subject operating system. In that, my topic is paging table, the structure of paging table. In that, let us know some introduction about the structure of paging table. We have the data structure that is used by the virtual memory system in the operating system of a computer in order to store the mapping between physical and logical addresses is commonly known as page table. Here we have the structure of page table. As we had already told you that the logical address that is generated by the CPU is translated into the physical address with the help of the page table. Thus, page table mainly provides the corresponding frame number, that is base address of the frame, where that page is stored in the main memory. We have the characteristics of the page table here. In that, some of the characteristics of page table are follows are: it is stored in the main memory, and it is generally the number of entries in the page table is equals to the number of pages in which the process is divided. The PTBR means the page table base register, and it is basically used to hold the base address for the page table of the current process, and that each process has its own independent page table. And we have the techniques used for structuring the page table. Some of the common techniques that are used for structuring the page table are as follows: hierarchical paging, hashed page tables, inverted page tables. When it comes to hierarchical paging, another name of hierarchical paging is multi-level paging. There might be a case where the page table is too big to fit in a contiguous space, so we may have a hierarchy with several levels. In this type of paging, the logical address space is broken up into multiple page tables. This hierarchical paging is one of the simplest techniques, and for this purpose, a two-level page table and three-level page table can be used. When it comes to two-level page table, consider a system having 32-bit logical address space and a page size of 1 KB, and it is further divided into page number and page offset. That is the page number consisting of 22 bits and the page offset consisting of 10 bits. As we page the page table, the page number is further divided into page number and page offset. It consists page number consisting of 12 bits and page offset consisting of 10 bits. And this, the logical address is follows as page number P1 and P2 and page offset is D. In the above diagram, P1 is an index into the outer page table and P2 indicates the displacement within the page of the inner page table. As address translation works from outer page table inward, so is known as forward mapped page table. This given figure below shows that the address translation scheme for two-level page table. We have the logical address P1, P2 and D. This P1 goes to outer page table and P2 goes to page of page table. It gives the output as D. And we have the three-level page table. This for a system with 64-bit logical address space. A two-level paging scheme is not appropriate. Let us suppose that the page size in the case is 4 KB. If in this case we will use the two-page level scheme, then the addresses will look like this, where the outer page is P1 and inner page is P2 and offset is D. And thus, in order to avoid a large table, there is a solution, and that is to divide the outer page table, and then it will result in a three-level page table. When we give second outer page as P1 and outer page as P2, inner page as P2, the offset gives the T. We have it will result in three-level page table here. When come to hashed page tables, these hashed page tables approach is used to handle addresses space that are larger than 32 bits. In this virtual page, the number is hashed into a page table. This page table mainly contains a chain of elements hashing to the same elements. Each element mainly consisting of three parts, that is the virtual page number and the third value of the mapping page frame, a pointer to the next element in the linked list. Here we have the image, that is hash function, physical address and physical memory. hash table we have in this image. When come to clustered page tables, these are similar to hash tables, but here each entry refers to several pages, that is 16 rather than one. Mainly used for sparse address spaces where memory references are non-contiguous and scattered. We have here that is inverted page tables. The inverted page tables basically combines a page table and a frame table into a single data structure. There is one entry for each virtual page number and a real page of memory, and the entry mainly consisting of the virtual address of the page stored in that real memory location, along with the information about the process that owns the page. Even though this technique decreases the memory that is needed to store each page table, but it also increases the time that is needed to search the table whenever a page reference occurs. When come to the implementation of page table, we have the page table is kept in a memory. Page table base register points to the page table, and page table length register indicates size of the page table. In this scheme, every data or instruction access requires two memory access, one for the page table and one for the data instruction. The two memory access problem can be solved by the use of a special fast lookup hardware cache called associative memory or translation look aside buffers. When come to hashed page tables, common in address spaces 32 bits, the virtual page number is hashed into a page table. This page table contains a chain of elements hashing to the same location. Each element contains the virtual page number, the value of mapped page frame, a pointer to the next element. Virtual page numbers are compared in this chain searching for a match. If a match is found, the corresponding physical frame is extracted. Variation for 64-bit addresses is clustered page tables and similar to hashed, but each entry of refers to several pages such as 16 rather than one, especially useful for sparse address spaces where memory references are non-contiguous and scattered. I'm going to conclude this structure of paging table topic. As we had already told you that the logical addresses that is generated by the CPU is translated into the physical address with the help of the page table. Thus, page table mainly provides the corresponding frame number, base address of the frame, where that page is stored in the main memory. And the page table contains the base address of each page inside the physical memory. It is then combined with page offset to get the actual address of the required data in the main memory. The page number is used as the index of the page table, which contains the base address which is in the frame number. Thank you.